So in this next video, we're going to talk about multiplying polynomials. But before I get started, I want to review a couple of vocabulary terms. The first vocabulary term is that of a factor. So a factor is any mathematical expression that's separated by a multiplication sign or division sign. Another vocabulary term that's important is the idea of a term. Terms are other mathematical expressions that are separated by addition or subtraction. So, for example, if I have an expression that's written as xy cubed plus 3x, I would say that there are two terms in this expression. There's the first term is the xy cubed term, and the second term is the 3x term, because they're separated by this plus sign. And then within each of these terms, I see that x is a factor, and I also see that y cubed is a factor. If I wanted to separate this out even more, this expression is equivalent to the expression x times y times y times y plus 3x. So you could say that y was a factor of the first term as well. So when talking about multiplying polynomials, we're going to start with the most basic form of multiplying polynomials, and this example is going to be of the distributive property. So the distributive property typically refers to one in which our leading coefficient is just a single value. So for example, 3 plus x times 2. Notice I have a factor of 3 that's separated by a multiplication sign with this other factor, x plus 2. And when I employ the distributive property, I see that this is exactly equivalent to 3 groups of x plus 2, which could be written as x plus 2 plus x plus 2 plus x plus 2. Now this is an inefficient way of writing it out, but I'm doing this to explicate the fact that it's really just 3 groups of this factor x plus 2. And if I wanted to simplify this, I can use the commutative property of addition to rearrange this. Addition can happen in any order that I want, and I get x plus x plus x. And I also get 2 plus 2 plus 2. And when I combine like terms, I see that I have 3 groups of x and 3 groups of 2, or I end up with 3x plus 6. This is exactly a longhand way of thinking about the distributive property. It's likely that when you see an expression like this, you would do the distributive property by applying 3 times x and 3 times 2, because really you're multiplying this second factor by 3. And you end up with 3x and 3 plus 2 gives us 6, which is what we expected. So that's an example of the distributive property. What happens when we multiply other types of polynomials? For example, let's say that we're multiplying the polynomial x minus 5 times x plus 2. In this example, you could think of this as the distributive property another time. I can think of this initial factor as a single factor that's multiplying times the x, and it's also multiplying by the plus 2. So one way to think about writing this out is to write it as x minus 5 times x minus 5 times x, and then I'm going to add the x minus 5 times 2. X minus 5 times 2. So really in this case, instead of having a 3 as my initial coefficient, I'm thinking of an x minus 5 as my initial coefficient. And now I apply the distributive property to each of these as well. And I see I get x times x, which is x squared, and then x times negative 5 is negative 5x. And the same thing happens over here. 2 times x gives me 2x, and then 2 times negative 5 gives me minus 10. I'm going to combine my like terms. In this case, I have a minus 5 and a positive 2x, and I end up with x squared minus 3x minus 10. This is probably not the way that you would think about doing this. Most people use an acronym FOIL that I loathe, and the reason why I loathe it is because it doesn't generalize to higher degree polynomials. I'm going to introduce this one more time, and this time we're going to look at the same example, but we're going to look at a visual representation of the multiplication of x minus 5 times x plus 2. So in my visual model, I'm thinking of, let's do a different example. I'm going to do x plus 5 just for the visual model. It doesn't generalize as well to negative values. So for this visual model, I'm thinking of along one length of a rectangle, it's going to have a length of x, and then it's going to have an additional 5 units at the end. So I'm representing x plus 5 as the length along the top of a rectangle, whereas the side of the rectangle is going to have a length of x, and it's also going to have the plus 2 represented by the 2 bricks down here. So what happens when we fill in the rest of the rectangle? This is called the array model of multiplication. What am I left with? This is a visual way to represent what's going on. So this square here is the area of x times x, which is given by x squared. Whereas these bars here, they're each x units in length, and there are 5 of them, which means that this shaded region is going to comprise of 5 groups of x, or 5x. This shaded region down here is 2 groups of x, which we can write as 2x. And then this region here has just these 10 squares, and I can count them to get to 10 squares. So all in all, what happens when I multiply x plus 5 times x plus 2? I'm left with an x squared, and I also have 5 x's, I have 2 x's, and then I have a group of 10. And altogether that gives me x squared plus 7x plus 10. Again, we could use the standard distributive property to visualize what's going on here as well. Finally, let's look at a bigger polynomial. So suppose I have a polynomial something like 3x to the 4th plus x cubed minus 2x squared plus 5. And let's say I want to multiply this really long polynomial by, let's say, x squared minus 1. In order to do this multiplication, I have to multiply term by term. Again, it's a generalized distributive property where every term in this factor has to be multiplied by every term in this factor. And one way to do this is to actually use the standard multiplication algorithm. And if I think of my place values, this is 3x to the 4th plus x cubed minus 2x squared plus 0 x's. I'm using this as a placeholder because this didn't have any x's, plus 5. And now I'm going to multiply that by, let's see, I have 0 x's here. I have an x squared plus 0 x's minus 1. And when I do my multiplication, this can just be like long multiplication that we've done in the past, and this will ensure that I multiply every term in this expression by every term in this expression. When I multiply this by -1, I see that I get -1 times 5 is -5, -1 times 0 x's give me 0 x's, -1 times -2x squared gives me positive 2x squared, -1 times x cubed gives me -x cubed, and -1 times 3x to the 4th gives me -3x to the 4th. I'm going to multiply everything by 0 for this 0 x's, and that would give me all zeros. So I'm going to omit that row. Maybe I could just write zeros for clarity's sake. But then when I multiply by the x squared times 5, I'm going to put this in the x squared placeholder because the coefficient is an x squared times 5. So I'm left with 5x squared times 0 x's gives me 0 x's cubed, and then x squared times -2x squared gives me -2x to the 4th, and then x squared times x cubed. Remember, this is x times x times x times x times x gives me an x to the 5th. And then my final term is going to be x squared times 3x to the 4th, which is 3x to the 6th. And now I can just sum, and thankfully all of my like terms are going to be in all of the columns, and I'm left with -5, 0 x's, I get a plus 7x squared, I get minus x cubed, negative 3x to the 4ths minus 2x to the 4ths is negative 5x to the 4ths, plus x to the 5th, plus 3x to the 6th. And this is my final answer of polynomial multiplication. There's nothing new here. It's just one way to keep track of how this multiplication has taken place, so we make sure that every factor in this term is multiplied by every factor in this term.